Welcome 爱学习的你 aboard. Your learning journey starts now. We observe these systems, these agentic workflows, where agents collaborate. But do they not often falter? Is it not due to the very instructions we give them, the prompts? If these are flawed, might errors not accumulate, hindering their true potential? This seems a significant challenge. So, if prompts are the crux, how might we improve them? We are presented with ProRefine. It proposes using feedback from LLMs themselves during operation, at inference time. Does this not seem a curious approach? To refine the guide while the task is being performed, without needing further training? What might be the implications of such a method? Let us examine this ProRefine more closely. It involves three distinct entities, all LLMs. One performs the task, another critiques its performance, and a third uses that critique to refine the initial instruction. It resembles a teacher guiding a student, does it not? But here, the teacher and student are both models, interacting dynamically. How might this dynamic interaction lead to better outcomes than static prompts? The process unfolds iteratively. An initial prompt is given. The task model generates an output. Then, crucially, the feedback model assesses this output. Based on this assessment, the optimizer model adjusts the prompt. This refined prompt then guides the next generation. Does this iterative cycle, this constant refinement based on feedback, hold the key to improving the reasoning process? What might be the advantages of this step-by-step approach compared to generating a single, potentially flawed output? Now, consider the role of a verifier. Shouldn't we know if the initial answer is correct before refining? ProRefine cleverly combines the roles of feedback and verification. It uses a single model for both. But how does this affect the outcome? They tested scenarios with and without a verifier, even with a perfect one. Does this suggest that the quality of the initial judgment, the verification, is paramount for the success of the refinement process? What happens if the feedback is based on an incorrect premise? How is this process controlled? Two parameters appear important: K, the number of tokens generated before seeking feedback, and N, the maximum number of refinement steps. Does controlling the granularity of feedback and the duration of optimization allow for fine-tuning the process? Perhaps too much feedback could be distracting, or too little might miss critical issues. And the computational resources required, a single O100 GPU? Is this a practical constraint, or merely a detail of the specific implementation? To test this idea, where did they apply it? They chose 5 datasets, each demanding multi-step reasoning, particularly in mathematics. Object counting, sorting words, solving math problems. Why these specific tasks? Do they represent the kind of challenges where a well-crafted prompt or a refined one would make a significant difference? Are these representative of the complex reasoning we seek in AI agents? Which models were put to the test? Smaller ones like Llama 3.21b and 3b, and a larger one, Llama 3.18b. The feedback and optimization relied on a very large model, Llama 3.170b. Why choose different sizes? Does this allow us to see how ProRefine affects models with varying capabilities? And what about the baselines? Comparing against simple COTI and TextGrad, which uses fine-tuning, provides a useful context. Were the choices of K equals 10 and N equals 25 arbitrary, or did they arise from prior exploration? What did the experiments reveal? The results presented suggest a significant improvement over the basic chain-of-thought method. In many cases, ProRefine surpasses even TextGrad, which employs supervised fine-tuning. More intriguingly, it seems to bridge the gap between smaller and larger models. Could this mean that ProRefine allows less powerful models to achieve performance comparable to much larger ones? If so, what does this imply about the efficiency and accessibility of high-performing AI? Let's look closer at the individual datasets. On word sorting, the gains are quite substantial. On GSM-8 improvements are significant across all models tested. However, on Aquarat, the results are mixed, sometimes showing gains, sometimes declines. Does this variability tell us something about the nature of the tasks themselves? Are some tasks more amenable to this kind of iterative refinement than others? What might explain the differing outcomes? Recall the discussion about the verifier. The results seem to confirm its importance. Using a perfect verifier yields the best outcomes, suggesting the potential ceiling. Even the standard ProRefine with a verifier performs significantly better than when no initial check is made. This implies that knowing whether the initial answer is wrong is essential for effective refinement. Without this guidance, might the process become aimless or inefficient? What does this tell us about the necessity of accurate assessment in the learning process? How many iterations did the process typically require? The graph shows the average number varies. Does this mean that the optimal number of refinement steps is not universal? Perhaps simpler tasks converge quickly, while complex ones need more iterations? The fixed value of n equals 25 used in experiments might be a starting point, but could adjusting k and n for each specific task lead to better performance or lower cost? What considerations should guide this tuning? Let us revisit our first question. Can textual feedback truly improve performance at inference time? The evidence presented suggests a resounding yes. The ability to bridge the performance gap between models is particularly noteworthy. Instead of always resorting to larger, more expensive models, could this method offer a way to enhance existing models? Does this provide a path towards more efficient AI deployment, especially when resources are limited? What does this tell us about the power of feedback itself? Our second question concerned model size. Do larger models inherently benefit more from this refinement process? The data seems to suggest so. The improvements observed increase as the model size increases from 1 billion to 3 billion to 8 billion parameters. Does this imply that the capacity to understand and act upon feedback is itself linked to the model's inherent complexity? For tasks requiring nuanced reasoning, might larger models simply be better equipped to leverage the feedback provided by ProRefine? And what of the third question regarding the verifier? The findings strongly suggest that a high-quality verifier is not just helpful, but crucial. It not only improves the final result, but also makes the refinement process more efficient by focusing efforts where needed. Does this highlight the importance of accurate assessment in any learning or improvement process? Could future work explore optimizers designed to directly maximize the verifier's score? What does this tell us about the interplay between evaluation and improvement? Beyond performance, what else does this approach offer? The feedback generated by LLM feedback provides a window into the model's reasoning. Can we learn from this? Does this transparency offer a form of interpretability? While tested primarily on reasoning tasks, the authors claim the principle is general. Could this method be applied to other domains, perhaps even creative writing or dialogue generation? The examples shown in the paper illustrate both successes and failures, reminding us that even sophisticated systems can err. However, is there no cost to this improvement? The text acknowledges that accuracy comes at the expense of computational resources. Each iteration requires multiple model calls. This presents a trade-off. When might we accept this higher cost for potentially better results? And conversely, when might the simpler, faster, zero-shot approach suffice? The ability to tune the number of iterations and feedback granularity offers flexibility. How should we decide the optimal balance? As with any inquiry, we must acknowledge the limits of this work. The computational cost, the reliance on a capable feedback model, the potential biases introduced by using LLMs for evaluation, these are all valid concerns. The current setup requires manual tuning of parameters. Could the system be made more self-sufficient? And how broadly does this method truly apply? These questions point towards avenues for future investigation. True understanding requires recognizing what we do not yet know. So, we have examined this ProRefine method. It offers a novel way to improve prompts dynamically using feedback, achieving notable gains without extensive training. It seems to bridge the gap between model sizes, potentially making powerful AI more accessible. Does this represent a significant step towards more efficient and adaptable intelligent systems? The journey of understanding continues. This exploration leaves us with further questions. How best do we guide these tools? Is feedback merely a tool for correction, or does it illuminate the path to deeper understanding?